In this lesson, we're going to quickly look at the difference between static friction force and kinetic friction force, along with coefficients of friction. There's a block resting on a horizontal surface, and we know there are forces going downwards of gravity, and one going upwards is the normal force. So let's quickly label those: force normal, force gravity. Although not drawn equally here, they would be equal to each other since we are at a horizontal surface. We then would do a force applied, and of course a friction force would oppose that. So let's label those. So this would be the force applied, and this of course would be force of friction. And we do know that the net force on this object, force net, would be equal force applied minus the force of friction. Now let's talk about force applied relative to force of friction before this object moves. So here's a graph. So if I apply a little force on this and I do not overcome static friction force, now remember static means not moving, all the intermolecular forces are still intact. Okay, and that force, let's say I apply this much. I'm on my graph about right here. Static friction force will just simply oppose that. Let me apply more force. Let's say I'm right here on my graph. But it's still not enough to have this object move. Well, my static friction force is now this value. And so on. If I keep applying more and more and more, at some point I'll reach a place on this graph where my force applied is the maximum I can apply before this object will start moving. So at the very peak here, this is going to be the maximum static friction force. And then afterwards, the intermolecular forces break, the object starts to slide. We notice that the amount of force required to keep this thing going now is less. And this is going to be the force of friction. And I'll put a little sub K there, meaning the kinetic friction force. So force of friction static is greater than force of friction kinetic. And what I mean by that, this is the maximum. So if I apply a force to get an object moving and my force stays at this value, my object should accelerate then, because now the applied force is greater than the friction force. Let's put that in our equation. Well, force net, of course, equals ma. What would be the force applied in this case? Well, it would equal the static friction force. So that would be mg for force normal multiplied by mu, and I'll put a sub s there, standing for static. And then minus, well, once it starts moving, the friction lowers to kinetic. So that would be mg mu sub k. And we do notice that m's would cross off in our expression. And if I factor out a g, the acceleration of this object is going to equal g multiplied by mu static minus mu k. And that's an easy calculation for us to do. But remember that static friction will always oppose your applied force. And once that's broken, you've got force static max. It does require less force to keep it going at constant velocity. If you don't decrease that force, you will accelerate. And this is the expression to calculate the acceleration of that object. And what about inclined planes? Well, let's look at the special case here where this object is not moving. So let's say I've got an incline here, and I'm going to increase the angle, keep going, until this object starts to move. Well, we can calculate a mu s in this fashion by doing something as simple as this. Let's review our forces on an inclined plane. We, of course, have gravity downwards and normal upwards. And remember that gravity is broken into x and y coordinates on an inclined plane. Let's see what we have. This, of course, would be force normal. This is force gravity y. This is force gravity x. And this, of course, is force gravity. This is our angle theta. Well, if we keep raising this up to a point where it just starts to accelerate, let's look at the case where just before it starts to move, we of course have force gravity x pulling down the incline, and we have friction going upwards. So if we look at the maximum angle we can pull this thing up at before this box starts to slide, this is our net diagram. Here would be force net equals force friction minus force gravity x. Well, we know that normal and gravity y equal each other. So that's what we'll plug in for our friction force, force normal mu, and force gravity x is pulling down the incline. Let's go ahead and plug this in. If this has a mass of m, then we just have m times 0, because we're not accelerating it, equals friction force, would then be force gravity cosine theta multiplied by mu minus force gravity sine theta. Well, I can take this one to the other side, and I'm left with force gravity sine theta equals force gravity cosine theta mu. And our force gravities will cross off on both sides, solving for mu. Mu is then going to equal sine theta over cosine theta. Or mu is equal to tangent theta. So how could we apply this? Well, what we could do is lift the incline up, record the angle just when the box starts to slide, and take the tangent of that angle, and that's going to be our mu s max. Once it starts moving, we can lower the incline and then measure the angle that keeps the box moving at constant velocity. And that's going to be our mu k. Because either case, where the box is not moving or it's going down at constant velocity, our acceleration will be 0. So it's a good theoretical way of determining a coefficient of friction. In practice, it proves to be a little more challenging because friction usually isn't that constant when you're sliding down an incline. You get lots of experimental errors. But in theory, this is a way that you could get the coefficients of static friction and kinetic friction.